I'm going to try and wrap my head around just how massive this star really is. And I have to warn you right now, I'm probably going to fail. Not because the science is complicated, not because the math is hard, but because what we are about to look at is so incomprehensibly, so unreasonably, so offensively large that the human brain simply was not built to process it. By the end of tonight, you will understand why. Right now, you think you know what big means? You have seen mountains, you have seen oceans, you have looked up at the sky and felt small. You have no idea what small actually feels like. Tonight on Dark Matter Nap, we are going to take your sense of scale, everything you think you understand about size, and we are going to dismantle it completely, layer by layer, star by star, until we get to the one that finishes the job entirely. Let's begin. Here is the real problem we need to talk about before we go anywhere. Your brain is broken. Not medically, not clinically, but cosmically, your brain is completely, fundamentally broken when it comes to understanding large numbers and large distances, and this is not your fault. This is evolution's fault. Your brain evolved over millions of years to solve very specific problems. How far is that predator? How high is that cliff? How many days of food do we have? Is that fruit ripe? Your brain is extraordinarily good at distances up to maybe a few miles. It is decent at distances up to a few hundred miles. Beyond that, it starts to struggle. And at astronomical scales, it simply gives up and replaces real comprehension with the word big, big, very big, really, very big, incredibly big. These are not understanding, these are surrender. These are your brain waving a white flag and substituting a feeling for a fact. Here is a simple test. Close your eyes and try to feel the difference between 1 million and 1 billion. You can't. Not really. They both just feel like a lot. But 1 billion is 1,000 millions. If you counted to 1 million, one number per second, it would take 11.5 days. To count to 1 billion at the same pace would take 32 years. 1 million. 1 billion. Your brain treats them almost identically. Both just feel large. Now imagine trying to comprehend the size of a star. A star, the kind of object we are going to look at tonight, is not a million times bigger than something familiar. It is not a billion times bigger. The numbers we are going to encounter tonight make a billion look quaint, make a billion look small, make a billion look like something you could hold in your hand. This is the challenge. This is why tonight is going to be genuinely hard, not because you are not intelligent enough, but because no human being, no matter how brilliant, no matter how scientifically trained, can truly feel the scale of what we are about to discuss. What we can do is build a series of stepping stones, a chain of comparisons, each one slightly more staggering than the last, that carries us from the world we understand to the one we cannot. That is what Dark Matter Nap is going to do tonight. So take a breath. Hold on to your sense of reality as long as you can, because it is not going to survive this video. Let's start somewhere familiar. Let's start with home, Earth. Our planet has a diameter of approximately 7,918 miles, nearly 8,000 miles from one side to the other, straight through the center. The circumference at the equator, the distance around the widest part, is about 24,901 miles. These are numbers most people have heard, but let's make them real. If you got in a car right now and drove at highway speed, let's say 60 miles per hour, without stopping, without sleeping, straight in one direction, how long would it take you to drive across the diameter of the Earth? About 132 hours. 5.5 days of continuous driving. To drive around the entire equator, about 415 hours, more than 17 days. That feels big. That feels genuinely large. Earth is big. Now let's look at it from space. When astronauts first saw Earth from the moon during the Apollo missions, they were struck by something that has been described by almost every astronaut who has experienced it, the overview effect. This profound, sometimes overwhelming realization of how small, how fragile, how impossibly alone our planet looks against the blackness of space. Astronaut Edgar Mitchell described it as an instant global consciousness. seeing Earth as a small, beautiful, blue marble hanging in the void, that marble, that pale blue dot, that is home, that is everything every human being has ever known or touched or built or loved. It fits in your field of view from 240,000 miles away. You can cover it with your thumb held at arm's length. Now, let's put something next to it. Let's put Jupiter. Jupiter, the largest planet in our solar system, has a diameter of approximately 86,881 miles. That is about 11 times the diameter of Earth. Not 11 miles bigger, 11 times bigger. If Earth were a grape, Jupiter would be a basketball. You could fit approximately 1,300 Earths inside Jupiter by volume. 1,300 Earths inside one planet. That is not a star yet. That is just a planet, a gas giant in our own solar system. Now let's put the Sun next to Jupiter. The Sun has a diameter of approximately 864,938 miles. That is about 10 times the diameter of Jupiter, about 109 times the diameter of Earth. If Earth were a marble, say, 1 centimeter across, the Sun would be a sphere about 109 centimeters in diameter, more than a meter, almost 4 feet across. And Earth would be that tiny marble sitting more than 117 meters away from it, nearly the length of a football field. That is the scale of our solar system. Earth, a marble, the Sun, a 4-foot sphere, more than a football field between them. You could fit approximately 1.3 million Earths inside the Sun. 1.3 million. Remember what I said about your brain replacing understanding with the word big? This is where it starts to happen. You read 1.3 million Earths and your brain says, "Oh, that's a lot," and moves on. Let's not move on. 1.3 million copies of our entire planet, everything you have ever known, every mountain, every ocean, every city, every person who has ever lived, all of that 1.3 million times over, packed inside a single star. And the Sun is not a large star. Let me say that again because it matters. Our Sun, the object that lights our sky, warms our planet, and makes all life on Earth possible, is an average star. Medium brightness, medium size, medium temperature. If you cataloged every star in the Milky Way galaxy, the Sun would sit somewhere in the middle of the size distribution, maybe slightly smaller than average. The Sun is not special. The Sun is not impressive by stellar standards. The Sun is the cosmic equivalent of a medium coffee, completely ordinary, and it contains 1.3 million Earths. Now we start climbing. If the Sun is average, what does above average look like? Let's start climbing the stellar size ladder. And I want you to keep that marble and football field image in your head as we go, because we are going to need it. Sirius, the brightest star in our night sky. Sirius is the brightest star visible in Earth's night sky. It sits about 8.6 light years away, relatively close in galactic terms. It is what astronomers call an A-type main sequence star, a bit hotter and more massive than the Sun. Sirius has a diameter roughly 1.7 times that of the Sun. So if the Sun is that 4-foot sphere in our marble comparison, Sirius is about a 6.5-foot sphere, taller than most people, brighter than our Sun by a factor of about 25. Not dramatically different. We are still in familiar territory, just slightly bigger, slightly brighter. Let's keep climbing. Vega, the star that was once the North Star. Vega is another well-known star. It served as the North Star about 12,000 years ago due to the wobble of Earth's axis, and it will be the North Star again in about 14,000 years. Vega has a diameter about 2.4 times that of the Sun. Still manageable, still within the range where your brain can hold the comparison. Pollux, a giant star nearby. Pollux, one of the twin stars in the constellation Gemini, is what astronomers classify as a giant star, a star that has expanded as it ages. Pollux has a diameter about 9 times that of the Sun. Now we are getting closer to the size of Jupiter relative to Earth, 9 times the Sun's diameter. Remember, the Sun already holds 1.3 million Earths. Pollux holds, let's not do that math yet. We are going much further. Arcturus, the giant you can see with your naked eye. Arcturus is one of the brightest stars in the northern hemisphere's night sky, an orange giant star about 37 light-years away. Arcturus has a diameter approximately 25 times that of the Sun. If the Sun were a basketball, Arcturus would be roughly a sphere 25 basketballs across. That is starting to become genuinely hard to picture. The volume comparison is even more striking, because volume scales with the cube of the diameter. A star 25 times wider than the Sun has a volume 25 cubed times larger. That is 15,625 times the Sun's volume, which means Arcturus could contain about 15,625 suns, or about 20 billion Earths. 20 billion Earths. Inside one star, we are not done climbing. Aldebaran, the Eye of the Bull. Aldebaran is the bright orange-red star that forms the Eye of Taurus the Bull. It is an evolved giant star, about 65 light-years away. Aldebaran has a diameter approximately 44 times that of the Sun. If you placed Aldebaran where our Sun is, it would extend beyond the orbit of Mercury. The innermost planet in our solar system would be inside the star. Think about that. Mercury, a whole planet, would be swallowed, consumed, existing inside the body of the star, and we still have not reached the truly large ones. Rigel, the supergiant. Rigel is the bright blue-white star in the constellation Orion, the lower right foot of the Hunter. It is a blue supergiant, one of the most luminous stars in the entire Milky Way galaxy. Rigel has a diameter approximately 78 times that of the Sun. Rigel is about 860 light-years away, and it is still one of the brightest stars in our night sky, which tells you something about how extraordinary its output is. It shines with a luminosity roughly 120,000 times greater than our Sun. If you replaced our Sun with Rigel, it would extend out to about 0.4 astronomical units, nearly halfway to Earth's orbit. Betelgeuse, when stars get truly terrifying. Now we arrive at one of the most famous stars in the night sky. Betelgeuse, the red supergiant forming the upper left shoulder of Orion. Betelgeuse has been making headlines in recent years because of its strange behavior. It dimmed significantly in 2019 and 2020 in what astronomers called the Great Dimming, leading to widespread speculation that it might be about to go supernova. It has not. Not yet, but it is a dying star, and it is enormous. Betelgeuse has a diameter approximately 700 to 1,000 times that of the Sun. The uncertainty is real. Betelgeuse is a variable star. Its size actually changes over time as it pulsates. Let's use 900 times as a working figure. 900 times the diameter of the Sun. If you placed Betelgeuse where our Sun is, centered at the same point in space, its surface would extend past the orbit of Mars. Earth would be deep inside the star. Mars would be inside the star. The asteroid belt would be inside the star. Our entire inner solar system, Mercury, Venus, Earth, Mars, swallowed, gone. Existing inside the body of a single star, from where we stand on Earth, we would not see a sun in the sky. We would be inside a star. The sky in every direction would be the glowing interior of a stellar atmosphere. Is your perspective starting to bend? Good, because we are not close to done. Everything we have seen so far from Sirius to Betelgeuse represents the range of stars that astronomers would call large to very large. Stars that are impressive by any measure. Stars whose scale genuinely challenges human comprehension. But the universe has been generous with its extremes. There are stars that make Betelgeuse look modest. Vi Canis Majoris, the star that rewrote records. For many years, Vi Canis Majoris held the title of the largest known star in the Milky Way. Located about 3,900 light-years away in the constellation Canis Major, Vi Canis Majoris is a red hypergiant, a category of star so extreme it required its own classification. Vi Canis Majoris has a diameter approximately 1,420 times that of the Sun. Let's go back to our marble comparison. Remember, Earth is a marble about 1 centimeter across. The Sun is a sphere about 109 centimeters across, just over a meter, positioned 117 meters away. In that same scale, Vy Canis Majoris would be a sphere about 1,550 meters across, nearly 1.5 miles in diameter, a sphere you could not see from one end to the other, a sphere large enough to contain an entire city inside it. If you replaced our Sun with Vi Canis Majoris, its surface would extend past the orbit of Jupiter, Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter all inside this one star. The volume comparison is staggering. Vi Canis Majoris has a volume approximately 2.9 billion times that of the Sun. You could fit 2.9 billion suns inside Vi Canis Majoris. 2.9 billion suns, each containing 1.3 million Earths. Your brain is giving up. It has already given up. The word big has completely collapsed into meaninglessness. What we are describing now is not big. It is a scale for which the human language of size has no adequate vocabulary. But Vi Canis Majoris is not the largest star we know of. Uyscuti, the long-reigning champion. For several years, Uyscuti held the record as the largest known star. Located about 9,500 light-years away in the constellation Scutum, Uyscuti is another red supergiant of extreme proportions. Uyscuti has a radius approximately 1,700 times that of the Sun, in diameter about 3,400 solar diameters. If Uyscuti replaced our Sun, its surface would extend to approximately 4.7 astronomical units from the center. Saturn orbits at about 9.5 aero-units. So Earth, Mars, Jupiter, all inside Uyscuti. Well inside. The distance from one side of Uyscuti to the other, its diameter, is approximately 2.4 billion kilometers. The diameter of Uyscuti is larger than the distance it takes light to travel in 2.2 hours. If you shone a flashlight from one side of this star toward the other side, the light would take over 2 hours to cross the star's diameter. Light, the fastest thing in the universe, traveling at 670 million miles per hour, would take 2 hours just to cross this one star. Let's put this in terms of travel time. If you could somehow board a commercial airplane, cruising at about 575 miles per hour, and fly across the diameter of Uyscuti at that speed, the journey would take approximately 900 years. 900 years of continuous flight across one star. Your brain has stopped. I know. That is okay. That is the correct response. But here is the thing. Uyscuti is not the largest anymore. In 2020, astronomers studying a star cluster called Stephenson 2, located about 20,000 light-years away in the constellation Scutum, identified a star that had been previously catalogued but not fully characterized. When they measured it properly, when they calculated its actual size, it became the new record holder. Stephenson 218, also called ST218, also called RSGC 218. And its size is so extreme that I need you to take everything we have built tonight, every comparison, every analogy, every stepping stone, and hold it in your mind simultaneously as I tell you what this star actually is. Stephenson 218 has a radius approximately 2,150 times that of the Sun, a diameter of approximately 4,300 solar diameters. Let's convert that to something real. The diameter of Stephenson 218 is approximately 3 billion kilometers. 3 billion kilometers from one side to the other. Our entire solar system, from the Sun to the orbit of Neptune, spans about 9 billion kilometers in diameter. So Stephenson 218 is roughly 1/3 the diameter of our entire solar system. If you placed Stephenson 218 at the center of our solar system, where the Sun sits, its surface would extend to approximately 9.3 astronomical units from the center. Saturn orbits at 9.5 astronomical units. Saturn, the ringed planet, the planet with a moon, Titan, that has a thicker atmosphere than Earth. Saturn, with its rings spanning 282,000 kilometers across. Saturn would be just barely outside the surface of this star, grazing the outer edge of its atmosphere. Everything inside Saturn's orbit, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, all of it would be inside this one star. Our home, the pale blue dot, the marble we started with tonight. It would be a microscopic speck floating somewhere deep inside the atmosphere of Stephenson 2-18, not orbiting it, not near it, inside it, submerged within it like a grain of dust in the middle of the Pacific Ocean. Let's do the volume comparison. Volume scales with the cube of the radius. Stephenson 2-18 has a radius 2,150 times that of the Sun. 2,150 cubed is approximately 9.9 billion. Stephenson 2-18 has a volume approximately 9.9 billion times that of the Sun. 9.9 billion suns would fit inside Stephenson 2-18. Each sun contains 1.3 million Earths. 9.9 billion times 1.3 million equals approximately 12.9 quadrillion Earths. 12.9 quadrillion, that is 12,900,000,000 Earths. Inside one star, go back to our marble. Earth is a marble, 1 centimeter across. The Sun is 109 centimeters, just over a meter. In that same scale, Stephenson 2-18 would be a sphere approximately 2,343 meters across, nearly 1.5 miles in diameter. A sphere so large that you could not see from one side to the other with the naked eye. A sphere you could not walk around in a day. And this sphere in our marble scale is located approximately 2.3 million meters from us, 2,300 kilometers away. About the distance from New York to Denver. That is how far away Stephenson 2-18 would be if Earth were a marble and the Sun were a meter-wide sphere. Our marble would be sitting in New York. Stephenson 2-18 would be a 1.5-mile wide sphere sitting in Denver. And if you could somehow travel to Stephenson 2-18, travel to its actual location in space, and if you could somehow survive on its surface, and if you then tried to fly a commercial airplane from one side of the star to the other, at 575 miles per hour, the journey would take approximately 1,100 years, over 1,000 years, of continuous flying across one star. Let's try another comparison. Light, 670 million miles per hour, the fastest thing that exists. If you shone a beam of light from one side of Stephenson 2-18 toward the other side, light would take approximately 8 hours and 23 minutes to cross the diameter. Our Sun, light crosses the Sun's diameter in about 4.6 seconds. Earth, light crosses Earth's diameter in about 0.04 seconds. Stephenson 2-18, over 8 hours. The light that left this star's far side when you woke up this morning would not reach the near side until you were going to sleep tonight. And this is one star, one object, in a galaxy of 200 to 400 billion stars, in a universe containing an estimated 2 trillion galaxies. Let me give you one more comparison, and this one is designed specifically to finish what we started tonight. We know Stephenson 2-18's radius is about 2,150 solar radii. The Sun's radius is about 695,700 kilometers. Stephenson 2-18's radius is therefore about 2,150 times 695,700 kilometers, approximately 1.5 billion kilometers. Earth's radius is 6,371 kilometers. Stephenson 2-18's radius compared to Earth's radius is approximately 1.5 billion divided by 6,371, about 235,000 times wider than Earth. If Earth were a marble 1 centimeter across, Stephenson 2-18 would be 2,350 meters across, nearly 1.5 miles. Now, imagine you are standing inside that marble. Your entire world, your whole planet, is 1 centimeter of space. Outside, 1.5 miles in every direction, is the surface of this star, your mountain ranges invisible, your oceans of film, your entire civilization less than a speck. The International Space Station orbits at about 400 kilometers above Earth's surface. On our marble scale, that is 0.0006 millimeters above the marble's surface. Less than the width of a human hair, divided by 1,000. The Moon, our closest neighbor, orbits Earth at about 384,000 kilometers. On our marble scale, that would be about 60 centimeters away, 2 feet, our pale blue dot, with the Moon 2 feet away. Inside a sphere 1.5 miles wide. This is the actual scale of our existence. This is how the universe actually measures us. We are not small. Small does not begin to cover it. We are microscopic. We are submicroscopic. We are a rounding error in the mathematics of a universe that produces objects like Stephenson 2-18 as a matter of routine. And yet, here we are, aware of it, looking up at the night sky and measuring the sizes of stars we will never reach, building telescopes and mathematics sophisticated enough to calculate the diameter of an object 20,000 light-years away, writing scripts and making videos about the incomprehensible scale of reality. The universe does not know we exist. Stephenson 2-18 does not know we are here. It has no awareness of the tiny pale blue marble in its corner of the galaxy. It is just fusing helium and shedding mass and slowly dying, as all massive stars do, completely indifferent to the fact that somewhere 20,000 light-years away, a species of upright mammals is trying to understand how big it is. But we know it exists. We measured it. We understood it, or at least we tried. That is the remarkable thing about tonight, not the star, the fact that we know about it. One final thought before we close. Stars like Stephenson 2-18, hypergiants, the most massive and extreme stars in the universe, do not live long by stellar standards. Our sun will live for about 10 billion years total. It is currently about 4.6 billion years into that lifespan. Hypergiants like Stephenson 2-18 burn their fuel so ferociously. Their luminosity is so extreme that they exhaust their nuclear fuel in a cosmological eye blink, a few million years, sometimes less. When they die, they do not go quietly. A star of this mass, at the end of its life, undergoes a catastrophic core collapse. The core, no longer supported by the outward pressure of nuclear fusion, falls inward in less than a second. The density becomes so extreme that the collapse rebounds violently outward. The result is a supernova explosion of almost incomprehensible energy. The explosion briefly outshines entire galaxies. For a few weeks, a dying star can emit more light than 100 billion suns combined. More energy than our sun will emit over its entire 10 billion year lifetime, released in a matter of days. And what is left behind? If the core is massive enough, above a certain threshold, it collapses past the neutron star stage entirely. It becomes a black hole, an object whose gravity is so extreme that not even light can escape, an object that tears a hole in the fabric of space-time itself. The largest stars in the universe, the ones that dwarf everything we have discussed tonight, end their lives by creating objects that defy our understanding of physics entirely. From the largest thing we know to the most extreme thing we know, in a single catastrophic moment. The universe does not do anything halfway. Tonight, we went from Earth, a pale blue marble, to Stephenson 2-18, a star so large that light takes over 8 hours to cross its diameter. We went from a planet you can drive across in 5 days to a star you cannot fly across in 1,000 years. We went from everything you have ever known to a scale your brain was never built to process. And here is what I want you to take away from Dark Matter Nap tonight. The universe is not just large. It is large in ways that permanently change how you see yourself once you truly understand them. You are not small in the way an ant is small compared to you. You are small in the way a single atom of hydrogen is small compared to an ocean. That is humbling. That is terrifying. That is wonderful. Because the thing that makes us different from every other object in this incomprehensible cosmos, from every asteroid, every planet, every giant star, is that we know. We look up, we measure, we wonder. In a universe that has no eyes, we are the eyes. In a universe that has no voice, Dark Matter Nap is trying to be one. Drop a comment right now. Tell me which comparison tonight actually broke your brain. Was it Betelgeuse swallowing our inner solar system? Was it the airplane flight across Stevenson 218 taking 1,000 years? Was it the light taking 8 hours to cross one star? Tell me below, because I read every single one. And if tonight changed how you see the night sky, subscribe to Dark Matter Nap, because every week we find something new to destroy your perspective with. And trust me, we are nowhere near done. Good night. Go look up Dark Matter Nap, where the universe gets real.